Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual ferment of the mid-20th century, Albert Einstein's general theory of relativity stood as a monumental achievement, a geometric description of gravity that had passed every observational test thrown at it. Yet, within its elegant field equations lay troubling, even pathological, solutions. These were the singularities, points of infinite density and spacetime curvature where the theory itself appeared to collapse. For decades, a prevailing sentiment among many physicists held that these mathematical oddities were mere artifacts of oversimplified models. The real universe, with its messy asymmetries and complex processes, would surely conspire to avoid such catastrophic endpoints. It took the profound intellectual upheaval of the 1960s, a gold age of gravitational physics, to dismantle this comforting belief. At the vanguard of this revolution was young Stephen Hawking, whose work, culminating in his influential contributions around 1971, including the essay on singularities in collapsing stars, irrevocably shifted our understanding. This work, alongside that of his colleague Roger Penrose, deployed powerful new mathematical techniques to demonstrate that singularities were a generic and unavoidable feature of general relativity, transforming black holes from a theoretical curiosity into a physical inevitability and setting the agenda for fundamental physics for the next half-century. The conceptual groundwork for Hawking's assault on the problem was laid by a generation of pioneers. The first realistic model of gravitational collapse was constructed in 1959 by J. Robert Oppenheimer and Hartland Snyder, building on earlier work with George Volkoff. Their solution described a pressureless sphere of dust contracting under its own gravity. The result was stark. The star collapsed indefinitely, eventually forming what we would now call an event horizon and crushing all its matter into a central singularity. While groundbreaking, the Oppenheimer-Snyder model was built upon a crucial, and deeply unrealistic, assumption of perfect spherical symmetry. This provided a convenient escape hatch for skeptics. Any small deviation from perfect sphericity, it was argued, would cause the collapsing matter to miss the central point, thereby avoiding the infinite density. The singularity was a product of the model's pristine geometry, a mathematical ghost that would vanish in the face of physical reality. This view held sway until the mid-1960s, when Roger Penrose introduced a radically new approach. Foregoing the messy business of solving Einstein's equations for specific, asymmetric cases, Penrose instead utilized the powerful tools of global differential geometry and topology. His 1965 paper presented a stunning theorem. It showed that if gravitational collapse proceeds far enough to form a trapped surface, a region of spacetime from which even light cannot escape, then a singularity is inescapable. A trapped surface is a closed two-dimensional surface, like a sphere, where both the outgoing and ingoing families of light rays orthogonal to the surface are converging. This is a profoundly counter-intuitive situation on the surface of an ordinary star. Outgoing light rays naturally diverge. The convergence of all light rays signifies that gravity has become so overwhelming that spacetime is collapsing in on itself. Penrose's genius was to show that the existence of such a surface, combined with a very general energy condition stating that gravity is always attractive, mathematically guaranteed the existence of incomplete geodesics, paths of particles or light that terminate abruptly. This termination point is the singularity. Crucially, Penrose's proof made no assumption of symmetry. Singularities were a robust prediction of the theory. Hawking, then a doctoral student, immediately recognized the power of Penrose's methods and masterfully applied a time-reversed version of the argument to the universe as a whole, demonstrating that the Big Bang itself must have originated from a singularity. Hawking's 1971 work on singularities in collapsing stars represented a powerful synthesis and extension of these revolutionary ideas. It presented a comprehensive case, built upon the rigorous mathematical framework he and Penrose had developed, that the formation of singularities was a generic outcome for massive stars. The argument, stripped to its conceptual core, is one of sublime logical force. It begins with the premise of a sufficiently massive star exhausting its nuclear fuel. Without the outward pressure from fusion, the star succumbs to its own immense gravitational pull and begins to collapse. As the star contracts, its surface gravity intensifies until it reaches a point of no return, forming a trapped surface and, consequently, an event horizon. At this juncture, the Penrose-Hawking theorems take hold. The theorems assert that any spacetime satisfying the strong energy condition, a physical assumption that the energy density, as measured by any observer, is always positive, and containing a trapped surface must be geodesically incomplete. This means that observers who cross the event horizon are on paths that have a finite end in their own future. Their world lines terminate. This endpoint, where the curvature of spacetime diverges to infinity and the density of matter becomes boundless, is the singularity. The immense power of this conclusion resides in its generality. It sidesteps the intricate details of the collapsing star's composition, its rotation, or its magnetic fields. The elegant, symmetric solutions of old were superseded by a topological argument of immense power. The singularity was a consequence of the causal structure of spacetime itself. Once gravity had become sufficiently dominant, the universe, according to general relativity, was disallowed from preventing its own breakdown under such extreme conditions. This had the wryly amusing effect of turning the tables on the skeptics. The burden of proof now fell upon them to demonstrate a plausible physical mechanism, some form of exotic matter violating the energy conditions that could avert the collapse. The immediate impact of this work was nothing short of a paradigm shift. The debate over the physical reality of black holes, a term recently coined by John Wheeler, effectively concluded within the domain of theoretical physics. The Penrose-Hawking singularity theorems elevated them from speculative objects, the ghosts in Einstein's machine, to fundamental predictions of our best theory of gravity. This newfound certainty catalyzed an explosion of research. If black holes were real, they must possess physical properties that could be studied and described. This led directly to the formulation of the laws of black hole mechanics. Hawking himself proved the celebrated area theorem, which states that the surface area of a black hole's event horizon can ever decrease over time, a striking parallel to the second law of thermodynamics. The focus of the field turned from questions of existence to questions of characterization. How do black holes interact with their surroundings? What happens when they merge? This theoretical groundwork provided the essential intellectual justification for the decades-long, arduous, and fantastically expensive experimental programs designed to detect them, culminating in the detection of gravitational waves from merging black holes by the LIGO collaboration, a triumphant vindication of the predictions made nearly half a century earlier. The certainty that these bizarre objects were a core part of the cosmic fabric, a certainty forged by the mathematical rigor of the singularity theorems, empowered generations of physicists to pursue their consequences with vigor. Yet, the most profound and enduring legacy of the singularity theorems is perhaps their role in highlighting the limits of the very theory from which they emerge. A singularity is a boundary where general relativity ceases to be a predictive science. The theory forecasts its own obsolescence. This classical prediction of infinite density and curvature was a giant finger pointing toward the need for new physics. It signaled the point where the smooth, geometric description of spacetime must give way to a more fundamental, quantum description. Hawking himself was among the first to pursue this implication with ferocious intensity. His work on singularities led him to ponder the behavior of quantum fields in the vicinity of an event horizon. He was initially skeptical of Jacob Bekenstein's audacious proposal that a black hole's surface area was a measure of its entropy. If an object has entropy, it must have a temperature and therefore it must radiate. This seemed to contradict the very definition of a black hole as an object from which nothing can escape. But by applying quantum field theory in curved spacetime, Hawking made his most startling discovery in 1974. Black holes are warm. They emit thermal radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This stunning result, which unites general relativity, quantum mechanics, and thermodynamics, grew directly from the classical foundation established by the singularity theorems. The classical certainty of collapse forced physicists to confront the quantum paradoxes it created, most notably the information loss paradox, which asks what happens to the information that falls into a black hole when it eventually evaporates. Furthermore, the singularity theorems gave birth to one of the great unresolved conjectures in physics, Penrose's cosmic censorship hypothesis. The theorems prove a singularity must form, but they leave open the question of whether it is always cloistered from view behind an event horizon. The hypothesis posits that nature abhors a naked singularity, ensuring that these points of physical lawlessness are forever hidden from the wider universe. Proving this remains a holy grail of mathematical physics, a direct intellectual descendant of the questions first posed with such clarity in the 1970s. In conclusion, Stephen Hawking's 1971 work on singularities, representing a pinnacle of the gold age of relativity, was a landmark of 20th century science. By wielding the abstract power of global geometry, it cemented the physical reality of black holes, transforming them from mathematical curiosities into central players in the cosmic drama. It closed the book on the classical debate over gravitational collapse, demonstrating with irrefutable logic that for massive stars, the end is an infinitesimal point of infinite density. But its greatest contribution was paradoxical. As a work firmly rooted in classical general relativity, it offered the most compelling argument that the theory was incomplete. By proving the existence of singularities, It defined the boundaries of its own validity and illuminated the path toward a deeper theory of quantum gravity. The paper stands as a testament to the idea that a theory's most profound insights are often found at its breaking points, where its predictions become so extreme that they signal the dawn of a new and more comprehensive understanding of the universe. It is a work whose intellectual reverberations continue to shape the frontiers of physics, a perfect classical prelude to the quantum questions that still animate our quest to understand the ultimate nature of reality.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.